out again. Sorry.
We're going to do the data. Good.
Nerding out again. Well, hey there, everybody. Welcome. Welcome once again to Astronomy Daily Live. I've got the kitty here. She is, I don't know what's going on with her, but the last couple of days she's been coming in here and, right before the live stream and just talks and talks and talks and talks and talks. And then as soon as I start, she's doing this now. So I don't know what's up with this. She's just doing her thing, I guess. So whatever it is, well, welcome everybody. Hope everybody's doing well. Everything's good here. No, you cannot have any of that. Ow. All right. So this is Astronomy Daily Live. So this is just a fun, casual get-together. We have our consumables of choice here. I've got the all hail the hydrogen hydroxide, right? And I've got a little bit of coffee left in here, so I'm doing that too. Is that okay? Does that pass your test? Thank you. We appreciate that. All right, well, cool. Hope everybody's doing well. I'm going to pop over in the chat again, make sure everything's going good over there. Good. All right. Well,
9-inch colors. I haven't seen them for a while.
Yeah, 9-inch colors. Hey, nice.
Yeah, she was. Yeah, I think he was here yesterday as well.
Was he?
Yeah, 9-inch colors was here either yesterday or the day before. I forget. That's one of the advantages of doing a daily live stream is that it's just I think Tom called it, right, a stream of consciousness stream, and that's all it is. So once it happens and then it just sort of goes by. So
yes.
Yeah, all right, well, cool. Nice to see 9-inch Cola's back. Like I said, everything is good here. As you can see, the sun is setting, although we've got clouds. We've got, this has been, weather-wise here, this has been a pretty kind of weird year. So, and it sort of continues to be a little bit weird. So, I don't know. That's, that's how it goes, though. Things change. And in fact, this live stream, if I sort of have my way, which isn't the only way, but it's, one way, that's actually what we're going to be looking at a little bit today, if you can see me at all. Are you enjoying being sort of the center of attention here? Yeah, she looks very, very proud of herself. All right, well, so I definitely want to say howdy. I cannot see them, so I have to look around here.
So my name is Bobby, and
I see Bobby. Hey.
Yeah, hello, and the lovely, sexy, talented, tricky Atalinta.
Ata, what's happening? Now you were
Nothing today. It is raining, so I'm inside playing with my toys.
Raining, so she's got toys now.
And I'm still training for that athletic event. Oh God.
Oh crud!
I smell like Ben Gay.
And show us that new toy you got, please.
I have. Wait a minute. I just put hand cream on. I'll drop it if I touch it.
Oh my gosh. But I have some good news. I have been enjoying pretty darn well with this radio.
Oh, yeah?
I think you've been having a lot of fun with that thing. I've been noticing, you've been posting a bunch of videos over on your YouTube channel. Hello. You're just gonna sit there the whole time, huh? So yeah, So you've been posting a few things over on your channel, Bobby, right?
Yeah. And one of the things I ever did, and I wish the host would sign on to it, is I actually use this radio in my phone to decode the radiogram show.
Wow, that's very cool. Very, very cool.
And
Ah,
there's the
there's
toy.
yeah. So there.
Toy.
Ha!
I
Look at
wouldn't
that.
let a kid touch
Don't,
this.
yeah, don't point that at us. That's no good. So what is that?
It's a Klingon bird of prey.
Oh,
Scale
okay.
model.
Very nice. Wow. So is that a model that you built, or is it just made that way?
No, this is not a model I built. This is one I purchased already built.
Nice.
From some Star Trek place. They have models, but if you start collecting the models yourself, everything you collect should be the same brand and build it yourself so they all match in size.
I gotcha. Right, right.
I mean,
So
I just decided I would take the lazy way out. And the thing I like about these, the models you build yourself are actually nicer, but these are programmed. Each ship is programmed with dialogue from a classic episode that the ship was in, and they pick one and do it. And I like that. But one of the problems with all this stuff, these collector's items, I found, not only do they cost as much as a used car, but not only are they expensive, but that's the minor problem. There's something wrong with every one you get. You have to fix it. I mean, I tried sending them back, and then I'd get another one, and there'd be something different wrong with it. So I thought, the hell with this. I'm getting my screwdriver out, go in there and fix it. And so, where I run into the real problems is on the older models. Because remember, I didn't have a Star Trek collection until a few months ago. Okay. So I ended up hunting around for old ones, originals, you know. And a lot of the people did dumb things, like they left the batteries in there for years.
Oh, okay, yeah,
Ooh, and that's a bad thing. You will never, if the time, leave the batteries, because as they age, they can have the tendency to leak out, and that can be your device.
Yeah, and that's it. I mean, in some cases, and some of it's fixable. You can. I soldered some new wiring in one of them. I'm pretty handy.
Oh yeah. And I think a lot of those, you know, I mean, with your kind of knowledge and skills and stuff, you know, I mean, and you know, if you have, you know, some basic electronics understanding and being able to solder and stuff, if you can bust into these things,
if you can,
usually fix them.
Well, I fixed all of mine. There was only one thing I couldn't fix. On a medical tricorder, little whizzer, I couldn't get that fixed. But otherwise, it's all right. Wait till I show up in my uniforms.
Oh my gosh!
Oh, this is sick.
I cannot.
I need help. There's no question about it.
No. We strongly encourage you to continue this path.
We have to do the data now.
Data.
Data. Let's do data.
Yeah. So trying to think if I didn't hear any astronomical news today. Really, nothing extraordinary or anything. You know, there's always crazy things. I think probably one of the nicest things, and you know, I didn't follow up on this at all, and I probably should. And it's sort of, I'm not exactly sure how this works. But the LSST, the Large Synoptic Survey Telescope, there's some kind of a thing going around. I'm not exactly sure if it's like a bill in Congress. I'm not sure if it's some kind of thing, but I guess some people want to rename the LSST after Vera Rubin.
Yeah.
And the funny thing is that if it's like a congressional bill, I don't know what kind of jurisdiction Congress has over the telescope. It's not going to be in the United States. I don't know if this is a national cooperation or like some kind of university cooperation of some sort. But I think it's very, very cool, to name those kinds of things after people, especially those who have made.
And that's one of the telescopes in operation, right?
No, not quite yet. Not quite yet. So yeah, I mean, it's really, really great, to recognize excellent work. And Vera Rubin, yeah, no kidding. She, as I recall, Vera Rubin was the lady who. Oh no, I'm going to get caught. Let's find out exactly who Vera Rubin is, because dang it, I didn't even think about it until just now. So I'm trying to think if she was around. She did some really, really neat work back in the 70s, or was it back in the 20s? I don't remember, but we're going to find out. Okay. So, of course.
So, Art Astro, welcome. Long time no see. The bill is simply a recommendation that, if passed into law, represents the will of the people of the United States of America. It has no real force, if he understands correctly.
Okay,
from the 60s to the 80s. And Pagemaster says she did work on evidence of dark matter.
That's what it was. It was galaxy rotation curves. Yeah, she was measuring the velocities of objects as they went around in the centers of galaxies. She was measuring the velocity, and as you measure the velocity as a function of distance from the center, if things are as we think they are, then the velocity curve should have a particular shape. And she gathered the data and worked on things to show that the actual velocities are quite different than expected. And so that's how we came up with this little bit of a fudge factor, which we're now calling dark matter, to sort of account for that. And it's a fudge factor. That's all it is.
It is nice to know my Congress is doing something, even if it has no force of law.
Yeah. No, these are the kinds of things that I really like to find out about and talk about a little bit, because it's those nice little things that just make the world great.
Yeah. And was that the one that should have won the Nobel Prize?
No, that was actually another.
No, that was another lady.
Yeah, I think that was
she ended up getting it later, and she gave it away. She ended up. She had a really nice attitude. She had a nice career anyway, and didn't need the money, and so.
Yeah.
I mean, she wasn't like all bitter and bent out of shape, because the bitterness itself can kill you. Trust me.
Yeah.
Saw that happen to a lot of women.
Yeah.
The bitterness destroyed the quality of life they could have had.
Yep. Yeah, and
Our Astro said that it was a Nobel Prize caliber work, but she didn't get the Nobel Prize,
No,
as it happened way too often.
Yep. Yeah. So hopefully we will, it'll begin to dawn on us that we really have to take into account half the population, and sort of get with it.
And may that be true. That could have happened with all kinds of lore shows as well.
Yeah. Anyway, Carolina Sky Astronomy. Hey, nice to see you in the chat.
Welcome, Jim. I just hate to see one that they actually gave it to the wrong type of people, and the next thing you know, their opponents goes backstage and charges down with blam and cause a big melee.
Yeah, most astronomers don't have that kind of problem, so most of them at least. All right, well, cheers. I don't have much coffee left, but I've got a full mug here.
Full tank of turpentine there.
Yes, sirree. Right up to the top. I'm not
see
talking.
that in live events now these days, especially in hockey.
Well, that's okay. I don't mind. Actually, I don't understand exactly why, but I really like rugby. Really like to watch rugby. And
that's where you get your savage macho rocks off, watching rugby. Oh,
I don't know.
That's brutal.
Actually, I do know exactly what it is. It's that I cannot understand it. I cannot. I don't know any of the rules. I don't know anything about it at all. I've been watching it for a pretty long time, and I can't figure it out. I just can't.
Yeah.
So
now, truth to be told, Atta, did you see the last fight that Conor McGregor did in Nevada, or no?
No, I didn't.
So Conor McGregor lost, and his opponent, after he beat Conor McGregor, he go up and had
Hey there, that looks like an ERRT.
Yeah.
Hey,
that's
what's going on?
Okay, so again, I was telling the
When they shut your electricity off?
No, I'm hiding in the dark again.
Okay. So Atta, as I was saying, so Conor McGregor lost to that Russian dude, and the Russian dude went up and attacked Conor man, and everything went berserk.
Oh, I bet. Oh, I wish I had seen it.
Yeah.
Now wait a minute.
They had to kick the fighters out of the arena as a result.
Ooh.
Wait a minute. Now
it was a very big, unacceptable melee.
You'll go for that, but you don't like rugby?
Now, just a minute. Women, I'm responding to the nature of my evolution. Women love to watch men fight. We always have. We always will.
Oh, okay. I was just checking.
What
about
just making sure?
What about like when women fight?
I don't like watching women fight. I mean, that doesn't do anything for me. It doesn't speak to my evolution.
I just don't like fighting whatsoever. It looks like it hurts. It looks like it hurts too much.
Soccer, a gentleman's game played by barbarians. Rugby, a barbarian's game played by gentlemen.
Yes.
Excellent. Excellent.
That is so incredibly true.
Now you can hear me.
It's really amazing how careful rugby players are. They because if when they're not, these guys get seriously hurt. and could probably easily get killed. Easy. So yeah, the rugby guys have to be careful. But that is a tangent that I am just going to pull in, and I was so yesterday we were looking at the orbital data of Earth and asteroid 1999 KW4. And this is the asteroid that just recently passed by us really close, back on, I don't know, like May 25th or 26th or so. And so what I was kind of interested in yesterday was just looking at 1 year's worth of data. And I think we looked 6 months before and 6 months after May 25th. So that'd be November 25th of 2018 to November 25th of 2019. So that time span. And I was kind of interested in seeing what the distance between Earth and this asteroid was during that time period. And that's about as far as we got yesterday. But what I was sort of keen on doing, and I actually didn't get around to it till this afternoon, is actually look at a longer time span to sort of see where all that went. Because it was sort of an interesting wiggly line, but it was just one sort of 1 year's worth. So what I did this afternoon is I went back to the JPL site, and I grabbed, I think I grabbed 25 years worth of motion instead, and I knocked it down to giving us the position every day instead of every hour, because that's just a lot of data. So yeah, why don't I show you that first, and then we'll go back to the 1 year's worth of data, and with that, I want to look at a couple other kind of interesting things and show you some stuff. We're actually going to be looking at some concepts of calculus here, and you won't even recognize it. But calculus is actually super easy. I say this in hindsight. While I was learning it, oh man, painful. But in hindsight, it's like, wow, that's really easy. So we'll look at all that. So all right, let me get this all set up here for you. So how are you, Ron? We didn't get a chance to say.
I'm so good.
Say howdy. Everything's good in your area.
Good. You were talking about the orbital of Earth, and you said Earth. I thought you meant Earth.
Well, the orbit of Earth and the orbit of Earth is pretty much the same.
Yeah.
Pretty much the same.
I think that Earth sounds better than Earth.
Okay, well, I think that is a valid opinion.
For today, I don't think Earth played Foo Fighters today. I played Foo Fighters today.
Oh, sweet.
Earth played Foo Fighters today, so I don't think Earth played that today.
Yeah, well, Earth usually plays a different game.
Yeah.
Okay, I'm going to share my screen. How do I do that?
But now there are musicians that listen to the sounds of the Earth, and they actually do songs, don't they, from the natural sounds?
Oh yeah, of course. I mean, a lot of I think a lot of that is the Earth's sounds is sort of outside of the acoustic range of our ears.
Right.
But we can shift up or shift down if we want to, and
different people have different vibrations they pick up on too. for
Cool.
different tones and things like that. You know.
Yeah, neat.
That makes sense.
All right, I'm going to share my screen
Uh-oh.
because I am ready.
Right.
I'm
Oh,
ready
there it
to
goes.
rock
There
and
it
roll.
goes.
We're going to go into the wormhole. Woohoo! We're going to go over here. Okay, so this is what we looked at yesterday. Was we got about this far. Let's plot.
No.
So what I did is I grabbed the X, Y, and Z distances of the Earth to the Sun, and
Yeah.
also
I got you.
and also this asteroid
Okay.
to the Sun, and we just sort of looked at that, and then I also calculated. I wrote a little Perl script here to calculate the distance between the Earth and this asteroid, and we looked at that, and that's what we're going to look at right now, just to remind you.
And Cosmic, and we'd like to welcome. Oh, we're in the Beta Taurus meteor shower. Where's the peak page?
Yeah, let us know. Yeah, the Taurids are kind of an interesting meteor shower too. So yeah, definitely check that out. There's the theory is that there's some pretty big chunks out there in this meteor shower. They think that the Tunguska event in 1908 might have been part of this shower.
I did say we'd like to welcome Kira H and Indy Cowley in the chat.
Andy Cowley and Kira H, nice to see you. We are nerding out again with some data that we were looking at last night, and we're going to do it again.
June 28th. Wow, the last Friday of the month.
Line width 1, line color 8. So this is what we got. So this is the distance between Earth and this asteroid, 1999 KW4, over the course of a year. So between November 25th of last year and November 25th of this year, it's sort of centered on its closest approach to us, which was May 25th. So this is what we got with that. I'm gonna blow this up a little bit here so it's a bit easier to see. And GNU plot is really cool. I can take it and rotate it around and stuff, so we can sort of see. You know, it probably begins here and ends here, but these values, these numbers here, and it sort of makes a little heart there. So these are distance in kilometers from each object. So if they were at, well, the coordinate 0, 0, 0, which is what? Here's 0, and here's 0. So somewhere up here, 0, 0, 0 would be the asteroid and the Earth are in the same place. So everything else means, you know, that they are in a different place. There's some kind of distance between them. So there's 1 year's worth of motion. But what I was interested in at the end of yesterday's live stream is what happens after multiple years. So I ran it for 25 years, and I think I ran it from 29. Yeah, I think I ran it from 2018 to 2040. No, 2023. I think. And I got this. Show you.
Hit us. You won't hit us.
Exactly the same. So this is exactly the same, except just run longer. So that's what we get.
Oh, spirograph.
Yeah, it's kind of a spirograph type of a thing.
I used to have one.
And again, yeah, it's sort of a three-dimensional one, though. You see that? But what this is showing, again, is distance between Earth and this asteroid.
We're safe, obviously.
What's that?
We're safe as far as it's not going to hit us.
I don't think, I was actually looking at that, and there are two near passes in the next 25 years, and we just experienced one. So there's actually going to be another near pass. I don't know exactly when, but it's about well, at least according to the calculations, the distance is going to be about the same as this last one. But yeah, they make these kind of interesting patterns, and I can.
When was the last time an asteroid did hit the Earth?
Well, it depends on what you define as an asteroid.
Right.
Things are hitting the Earth constantly. I think there are tens of thousands of tons of material falling down on Earth every single day. But if you're talking about sort of big things, that happens relatively often. Probably not every day, but maybe at least a couple times a week, you'll get a big one. They mostly come in when they're over the ocean, right? Because there's a 70% chance that's going to happen. So, those kinds of things are never really seen. But I think we sort of get a moderately big one. I don't know, maybe every 10 or 20 years. Anyway, I'm going to, let me get rid of the border and all the tick marks and all that, so we can really sort of focus in on the shape itself. So it's just kind of neat to rotate this around. So I've connected all the data points with lines, but my guess is that if I use points instead of lines, it's probably going to look about the same. Let's find out. Points, point type 7. Let's make it pretty small. Black. Yeah, it looks more or less about the same. So each of these dots is one day, like that. So okay, another interesting thing to do, and we can actually do this with this code that I wrote yesterday, is we can calculate the line of sight distance between these two objects. So let's do that. In order to do that, we're going to use a very, very famous equation, Pythagoras' theorem equation, I guess you'd call it. And what that looks like is something like this. I sort of have to do this in two parts. So let's call XXX. Well, actually, let's call it XX. So I'm going to square each of the X distances. XD times XD. And I'm going to zoom in a little bit here so you can maybe see it a little bit better. And I'm going to do that for Y and Z. So there's Y and there's Z. Change all these variables around. And then, let's see, we're going to, what should I call this? Let's call it RR. It's going to be the square root of xx plus yy plus zz. Like that.
Kind of a bit late for you to walk the dog, huh, Chuck?
Walking the dog. Gotta be done. Gotta be done. Okay, so that's just another column here in the outputs. So we'll be able to do that like line of sight distance versus Julian date, which is the first thing. So yeah, let's run that. Look at our history, and let's do them both. So this is a year's worth, and this is the 25 years worth. Let's go like that. So now we have, so this value here is just square root of this squared plus that squared plus that squared. That's how you get that number there. So that's just line of sight distance. It's like a vector distance. So let's plot that versus time, which is the Julian date over here on the left. So that's column 1, 2, 3, 4, 5. So column 1 and 5. Let's do that. Using 1 and 5. We'll just connect them with lines again. Lines. It's going to be kind of sinusoidal, I think. It should be. Line with 1. Line color black. Okay, yeah, it's so this is the line of sight distance between the Earth and this asteroid. This is November 25th of last year, and this is November 25th of this year. And as you can see, the distance sort of reaches a minimum right about there, and that was May 25th, I think is what that date is. So yeah, it's kind of interesting. It's radially, right now it's kind of moving away, but what, maybe in about 3 months or so, 2 months, it's going to actually radially start moving towards us again a little bit, and then it's going to race away. So that's just, because of the mutual orbits of these things. Yeah, that's just how it works out. It's kind of an interesting bump here too. So pretty cool, pretty cool. Now we can do this for 25 years too. We've got that data. Let's look at that. So this should just sort of be a repeating pattern, I think. I don't know. Oh, wow. All right. So, yeah, I mean, it's compressed because, we're looking at 25 years and not just 1 year. So you can sort of see 1 year's motion here, really, really narrow. But yeah, wow, that's kind of neat what's going on here. Yeah, kind of interesting. So let's look at year 1. So what I thought that we could do is start actually getting into a little bit of the calculus here and see how that goes. The easiest way to talk about this and to show this is to look at this data here. Let's just look at this. So here are the radial values in the line of sight distance between the Earth and this asteroid. But what we can do is we can take this second number and subtract it from the first. And what we get after analysis, what we'll get is a new
He's out of playing with her
distance.
toys over there.
Yeah.
That's
So
not bad.
yeah, so this is how much the distance has changed between this date and this date. Well, a distance over time is a velocity. So actually, the difference between these two values is a velocity. And we can do that.
How far is that between the 84 and the 26? The second number, you got the 84, whatever it is, and then you got the 26, whatever. Yeah, the second half of that number. What's the distance?
Oh, well, I'm not sure.
Or you see the distance between the first number and the second number?
Yeah. It looks like it's going to be, what, maybe about 40,000 kilometers or so, if I do a rough subtraction in my head.
Do they use kilometers in space? I'm just kidding.
They do. They do. So yeah,
that's funny. I never heard them say that in Star Trek. I never heard them say kilometers in Star Trek.
Yeah, what did they use?
They used I don't know.
You know what? I think they did. I think they used the metric system.
Really?
Star Trek. I think so. So, Atta, do you have any idea?
No, but I bet Page Master knows. I think you're right. I think it is metric.
I think so. Anyway, so if you simply subtract this
even though the Klingons especially just uses kilograms, which I think it is the Klingon metric system.
It probably is. Yeah. So yeah, so
the difference between those two. And where's your calculator at? Get your calculator out.
Well, I write some code to calculate all of these things because that there are 8,761 of these data points, and I'm not going to do that by hand. But yeah, by simply subtracting these two, I will get a number of kilometers per hour in this case. Because these are separated by 1 hour. So let's do that. We can use almost exactly the same code. Let's call it.
Can't you just use a calculator?
No, not for 8,761 of them.
No, I guess not. You just said you had to subtract one from another.
Oh, okay, yeah.
You're talking about one.
Gotcha.
Right.
Yeah.
One at a time, right?
Right. What I'm going to do, and yeah, I completely forgot to mention this, is I'm going to take this number and subtract it from that number, and then I'm going to take this number and subtract it from that.
Okay, you're going to do them all and get an average, right?
No.
No.
I'm simply going to take that number and subtract it from that one, and then I'm going to write it out.
That's what I thought you were going to do.
And then I'm going to do that.
But who came up with all this data?
That minus that. What's that, Ron?
Who came up with all this data?
So this is data from the JPL Horizons website.
Yeah, he got it off the website.
Yeah. So these are calculated values based on the orbits and all that. So these aren't actually observed, but they're extremely close to what they actually are.
Are they using like a radio telescope to get these information?
No, all these numbers are calculated, all of them. So you can take
But
the orbits.
the same way that we would calculate the orbit of the moon, for instance.
Exactly.
The same idea. Maybe a
Yeah.
little bit more stretched out because it's farther away, but it's the same process.
Same thing. Yep.
Okay.
Same exact thing. So yeah. So I'm just going to take that number, subtract it from that, write out the result. And then I'm going to take that one and subtract it from that one, the previous one, and I'll write that out. And then I'll do that one minus that
Here's a
one.
good question. Now,
et cetera, et cetera.
Halley's Comet, whatever you want to call it.
Yeah.
People call it different from different parts of the country.
Yeah.
Anyway, it was around here in 85, was it?
85, 86.
I was in I missed it. I didn't get to see it, darn it. But anyway, I have to wait till
You're not going to get to see it the next time.
No, I'll get to see it when I'm up there. When I'm up there with it.
Or you could have a lot better view.
I'm pushing it around, you guys
That's
are
right.
thinking just flying around by itself. No, they got people up there pushing it.
They've got pushers.
No, no. So, but it comes around every 75 years, apparently, and they got this figured out. What was it, 1906 or whatever time it was right before that,
1910. Yep.
Somewhere around there. I'm just trying to remember the dates that I remember from the history lesson about it.
Yeah.
Then of course, 86, or 85, and then of course it's not gonna be around for another 75 years. Let's see.
Right.
When is that?
86
and 75. I don't know.
Well, I'm gonna grab my calculator here.
Oh yeah, we got him to grab calculator.
1986 plus. I think it's actually like 76 years. So that puts it at 2062.
Well, I don't know.
I'll be there, but I'll be around.
Well, I might be there. I don't know.
I will.
Ron, you never saw my radio, right?
No, I didn't. Oh, yeah, okay. Cool.
Cool. All right. I need to actually keep these distances. Whoa, how am I going to do that? This is getting complicated. No, it's actually not. Yeah. Okay. So I'm going to change this a little bit because we don't need two of these anymore. That can stay the same. That can stay.
123 then, Ert.
Okay.
I'll get there. I don't think they'll get there.
I'll be 123 in my prime.
Yeah,
in your prime.
I'll be right behind you at about probably 90 something from that old if I live that long.
Yeah. Well, there's a goal there for you.
Yeah, I don't think. I think my health issues are too far gone already. I don't think I'll make that long.
Well, like I say,
my goal was once 100 years old, and then when I figured out I wasn't going to make it, I said, I won't say the other word, but anyway, let's just say.
There you go. All right, so I think it's all.
Well, each day is your last, and you just enjoy every day as it is.
Exactly.
And then,
exactly.
Hopefully you have a good day at it, and everybody has fun, and we all get along. Hopefully we all just get along.
Yeah.
So.
Where have I heard that before?
Well, there's so many times I've been dealing with people's attitudes and everything like that. You had to straighten them out a couple times.
Yeah. Okay, so
what do you got?
So here's the magical part. As you can see, I'm starting this for loop at 1, not at 0, because what I'm going to do is I'm going to take the current value and subtract it from the previous value, like m minus 1, like that. So this will take value 0 and subtract value, or sorry, value 1 and subtract value 0 from it. So that will, at least in this first iteration, that will calculate our velocities as a function of time, at least radial velocity. And we could get really, really fancy and do the x, y, and z velocities instead. And I'm wondering if we should do that instead of this radial velocity thing. Could be, yeah, dang it. You know what? I think we need to do that. Let's do it. It's not too painful. Let's see. We want this to be 2, 3, and 2, 3, and 4. What is it? 0, 1, 2, and 3. Yeah, 0, 1, 2, and 3. What we want, because this is the x, y, and z here. So, okay. So 1, 2, and 3, like that. Okay. So then all we have to do is, let's do that, and that, and that. And, come on. Come on. Bad typing day. So we're going to do that. So each x, whoop, this has got to go to an I. Okay, I think that's right. That's right. So this will give us the velocity in x, the velocity in y, and the velocity in z. And that, yeah, that's probably a little bit more interesting to look at. So another way to say that this is going to be the velocity is to also say that it is the first derivative of the position. So change in position over time is velocity, which is dx dt. So it's just a derivative. We are actually calculating derivatives here. And it's all a derivative is a difference. All a derivative is. Simple as that. So this first derivative is called velocity or speed. But let me go over here. This I thought was kind of interesting. I found this this little chart, which I'll open up here. So these are the different names for derivatives of position. So the zeroth derivative of position is just position. The first derivative is called velocity. Then there's acceleration. Then it gets a little weird. Called jerk is the third derivative. Jounce or snap is the fourth. Crackle is the fifth derivative. Then pop, then lock, and then drop. So they have names for out to the eighth derivative of position. But we can also go the other way. We can do negative derivatives, which are the integrals. So these things are just like fancy adding. So derivatives are fancy subtraction. The integral is just fancy adding. That's all it is. And they have some really, really weird names for that as well. I don't even know how to pronounce that. Absment? I'm not quite sure.
You're just doing straight velocity, aren't you?
Warp factor 1, Captain.
Well, this is what we're going to start with.
Okay.
But I want to look at all of these, see what happens. So, yeah, let's look at the velocity first.
Yeah, I'd just like to see one of them.
Mm-hmm. All right. I think we're there. Yeah, I think so. Let's run it and find out.
The moment of truth here.
Yeah, I'll put. We'll call it. I'll put A. I'll put A. Oh,
Yeah.
okay. Let's. I
Crap.
don't need all of those. Why did that?
Tom, we can use you back in the panel.
Huh. It's all 0. I'm not quite sure why.
Uh-oh. No, that can't be right.
No, that's definitely not right. M-1, dollar M-1. That's right. Easy. Oh, I'm not quite sure what I'm missing here. That's all right. That's all okay.
Looks like to me you better be emailing Tom.
M-1. I'm not quite sure what's wrong with that. I don't see anything wrong with
Abasement
that.
is a combined word of absence and displacement.
Okay, cool. Let's see if this fixes it, although I don't think I have to do this. Oh. M-1. Whoop.
Here we go.
Nope. What am I doing wrong here?
Man.
I'm not quite sure. This is a pretty simple exercise, so, well, my apologies for not, there must be a typo or something somewhere, because that's, yeah, that's exactly how it's supposed to be. I'm not seeing anything obvious here. Dang. Well, maybe I will have to use my calculator on this. All 8,761 of them.
Similarly, abscission, combined words of abscess, absence, and position.
Very cool. I don't think this will make any difference, but let me do this anyway.
Surprised they didn't have a Rice Krispies on there.
What's that?
Crackle on top. Snap, crackle on top. There are Rice Krispies on there.
Yeah. Well, and if we can, I want to show you those with this data. We just have to sort of get over my...
You remember the commercial, all right?
What's that?
Snap, crackle on pop, Rice Krispies.
Yeah.
Yeah, I remember that.
I'm not going to try to sing it. No way.
Oh, is there a song associated with that?
Yeah.
I don't remember the song.
There was.
There was? Wow, I don't remember that one.
You can find it on YouTube.
Okay. I will have to look. Wow, I don't know. I'm really not quite sure why this isn't working. Because that
Because you're thinking about cereal now, you're not thinking about the equation.
Yeah, that's probably it. Let's do this one. One. Nope. Well, what am I doing wrong here? Let's do this. So
nobody ordered a Earth Radio mug.
What's that?
Nobody wanted to order an Earth Radio mug.
Well, not yet, but I'm thinking about it.
Okay, or I'll get on. I'll get on there and order it. I buy everything. Why shouldn't I buy your mug?
Buys everything. Oh, this is why.
I'm trying to die broke, you know.
Because this data, there are no commas in between each thing. It's a space.
Oh.
So
that's
why.
Oh crap! You dummy.
Well, now be nice, Bobby.
Yeah, that's the trouble with programming. I mean, you know, you're talking to a machine. For
that's what I don't like about doing Linux when I was using Linux, you know, or Ubuntu, whatever you want to call it, same thing.
Right.
You sit there.
There we go.
If you didn't quite code it correctly, you miss one little thing, and then the whole thing was messed up.
Oh, sure. Yeah, that's how it is.
Or like when you're doing, like when I do on the website, you know, and it's like, I don't know why that didn't go up, and then you go back, oh, I forgot that word, or I forgot that letter.
One little character, just like what I was just doing. One character off doesn't work because it's doing exactly what it's being told. That's it.
Yeah.
So we're going to look at this. So this is now, instead of distance, XYZ distance, this is XYZ velocities. So it's sort of a different space. It's a velocity space. So 1, 2, 3, and 4. So this is a velocity space plot now. Output A using 2, 3, 4 with lines. Line with 1, line color black. Okay, let's take a look at that.
Bam.
Move it over here, blow it up a little bit. Okay. So now you're seeing how its velocity, or I guess, let's see, what would this be? This would be the change in X, Y, and Z distance versus time. So yeah, this is a velocity. It's kind of a weird kind of a velocity, but there it is. And as you can see, this little point right here, where it's sort of closest to 0 on all 3 axes, that was closest approach. So very cool.
All right.
Let's look at this in a slightly different way. Let's just look at the x velocity versus time. Oh, window went away. Woo! Let's see, can I do this? Is it 1 and 2? I think it's 1 and 2. Yeah, how can I do this? Let's do this. Multi-plot, plot, layout, 2-1. I think it's 2-1. Now let's try. Whoop. Set multi-plot, and let's do this one.
That's a lot of work.
I don't know if these are going to line up or not all that well, but multi-plot.
Ah.
So these kind of lined up pretty much exactly the same. So time is along the x-axis, and in the top plot you have the x distance, and in the bottom plot you have the x velocity. So as you can see, when the velocity bottoms out, am I doing that right? Yeah. This change here is a constant, so it's constantly going down. But as you can see here, as the position is changing really, really fast, the velocity goes up. So yeah, that's kind of interesting. Let's so that's x. Let's look at y the same way. We're going to do 1 and 3. That. And then this one. As you can see, one can spend hours and hours and hours and hours just playing with all this stuff. Pretty fun. So there's the y distance and the y velocity.
Kirk Enterprise, come in. Kirk Enterprise.
Kirk Enterprise. So yeah, see here the position isn't changing very much, and the velocity is really, really close to 0.
Mm-hmm.
When the position changes a lot, the velocity either goes really, really fast one way or fast another way. Pretty cool. So we can keep doing this. So we can take this, the velocities, and I guess what I should do is one more thing here.
Yeah.
Which is,
and one more thing, physics jerk is the rate of change of acceleration.
Yes. Yeah, it's just, what we're doing here is we are looking at the differences, which are just the first derivatives. All right, so let's do xx times xx. Whoop, wow, that was really off. That z y z z. And we're going to do, let's do, don't you love these incredibly descriptive variable names? y2 plus z2. That, and, say 1, 2, 3, 4, 5. Is it supposed to be 5? Yeah. Okay, so let's run this one more time. So we'll get exactly the same format as the previous one. So now we need to rename this. Let's do this. Let's go velocity. Okay, so now we can actually take velocity and calculate its derivative, which is going to be the acceleration. And I think this should work. I think it did. So here's the Julian date, and then here's now the x, y, and z acceleration in kilometers per minute per minute. So the velocity is kilometers per minute. This is now kilometers per minute per minute. So it's how the velocity is changing. So let's plot that. Should look kind of interesting, I guess. Let's do the x acceleration. Ooh. So there are places where it's accelerating very, very much, and then it suddenly decelerates. Wow, bam. So that's a very, very rapid deceleration, right? It's going from about 1,200 kilometers per minute in one direction to 600 kilometers per minute in the opposite direction. Pretty amazing. So we can keep doing this. What's the next one called? Jerk. Let's look at the jerk. Okay, so the third derivative of position.
It's almost like the name that Steve Martin called his dog in the movie The Jerk.
Yeah.
I'm going to cuss now. He called his dog Shithead. But that's the name of the dog, though. And
I don't think that I would call it jerk. I would call it bump.
That's exactly the dog Shithead, though, because the dog got everybody up, and it wasn't even nothing wrong. No, that's what they called the dog. Why did you wake everybody up at 2 o'clock in the morning?
Yeah. All right, so I'm going to calculate jerk here.
If you ever see that movie again, it is pretty funny.
Cool.
It's one of those things that you have to watch it, and then you think about it, like, a couple of days later, and you think, oh, now I got it.
Yeah. That's the sign of a good movie.
Then it's really funny, though, after you figure that out.
Exactly.
Like when you watch the movie, it's not that funny, though. But when you think about it afterwards, it's like,
Yeah. So as you can see, these numbers are getting smaller and smaller and smaller.
Oh, yeah. They're getting closer? It's getting closer?
Well, no. It's just that that's sort of what happens when you start looking at the differences of differences of differences of differences. The numbers just naturally get smaller and smaller and smaller. Now, the units on jerk, in this case, are kilometers per minute per minute per minute. So it's the change in acceleration. So it's really, really small, but as you'll see, it's got kind of an interesting shape, or it probably does. Yeah.
How's your water supply over there?
What's that, Ron?
How's your water supply? Is it getting low?
Oh, you know what? It's not.
I knew it was about that time. I was watching.
So we can just keep doing this and doing this and doing this until we get into the noise of the data itself. And that happens, I think, at about the 6th derivative. So let's just finish this out, and then we'll call it a day. So the next one is called jounce. So let's look at jounce. And this is called jerk. And you know what? I'm going to run these through here. So the next one's called crackle. Crackle. And this is going to be jounce. And let's do the pop as well. I think by the time we get to pop, it's going to look pretty poppy. Crackle. not crapple, crackle.
I like wood.
Yeah.
Okay, so let's take a look at these. Let's see what these. So jounce.
So what was that one that came in and it took off the different angle that they couldn't figure it out? The one with the Hawaiian name. I don't even know how to say
Oh
it.
yeah, you're talking about Oumuamua.
Yeah.
Yeah.
And came in and then it just kind of like bounced off and went out the other way somehow.
Yeah,
What's that about?
it was on what's called a hyperbolic orbit. So that means it is coming from way out there.
So I think it's like one of those ones that I would be pushing around, like I would just like kick it somewhere.
Yeah, no, it's gone. It's on its way out.
Yeah. That's kind of weird. It just kind of like shifted direction. Like everyone thought, oh, maybe it was some kind of a scout ship from somewhere. Well,
Yeah, it did. As far as I know, it did not shift from its once they figured out the orbit, I don't think it made any kind of changes at all. That would have been way too exciting. Okay, so there's crackle. As you can see, these numbers are getting really small, and kind of not very interesting anymore. And really physically, what does the fifth derivative? I mean, how do you describe that? I mean, what does it feel like? I don't know. So let's look at pop. The sixth derivative. So here, we're starting to get into the noise a little bit of the data itself. But yeah, so kind of interesting. So that's calculus. Those are derivatives. We're looking at the derivatives of a function. What do we start with?
I barely got algebra.
I think it was that. Is it that one? I think it was this one.
And that was with a G. A G minus.
So yeah.
They just let me go because they didn't want to see me again.
There you go.
You passed. You got a D minus. You go.
So there's the x distance between the Earth and this asteroid as a function of time, and this is
math anyway.
And this is the sixth derivative of that. So yeah, it's a major nerding out thing here, but it must be done, from time to time. Kind of neat stuff.
Don't get a heart attack with that type of data.
No, I don't think that's going to happen anytime soon. All right, everybody, I'm going to get out of here. I'm going to crash and burn. I'm
going to say something real quick though. That math can be used. Math is universal, like music, right? And so math can be used on functional, like music. You use some kind of formula, right?
Yep. Yeah.
Okay. And then with math, of course, you use a formula, but now to figure out different things like the motion of a planet, you use that formula, right?
That's right. Exactly.
So it's a universal language is what I was getting at.
It's sort of a universal.
Has a little poster on the wall in one of the South Park pictures. Yeah. One of the shows. Math is universal language, I think it says.
Yeah, I would call it a universal tool. I think language is that's a real stretch.
Yeah.
It's definitely an incredible tool. I think a lot of times math is sort of switched with reality. Those are two different things. Mathematics is fantasy land.
Mm-hmm.
It's pure fantasy land. But it's okay because it sort of, lets us know sort of what we think is going on. So that's okay. No, it's a great, great, great tool. Anyway, I'm going to get out of here because I'm going to crash and burn. So I will see you all again. I'll be back here again tomorrow, 2 hours UTC. Yep. Live long and prosper. Hope everybody has a great evening, great day, and more astronomy. I think the nerding out is done for now, but it will come back, guaranteed. Guaranteed. It can't be helped. Can't be helped. So, everybody, take care.
Well, all right.
That's right.
Yeah, good night.
I'll see you later.
Next time.
See you on the spin. Bye.
All right.